So now relative motion, and this is something that you probably saw in Physics 1, probably sort of briefly, but it's going to be a big deal in this class. So we've been doing all these, okay, just imagine. We've been doing all of our calculations dealing with a coordinate system that's not rotating and tracking the motion of objects as seen in that coordinate system. And you can imagine the coordinate system as a video camera, and it's like as the object moves around, this video camera is tracking its location as time goes by. So now imagine two separate non-rotating coordinate systems. With the same orientation. And each one is tracking the same object.
When you say tracking, you mean the camera is moving along with the object?
No, it's just keeping track of the location. Each one is, okay, let me change that. Each one is measuring the location. Okay. So here's our first coordinate system. I'm going to call this coordinate system A. And here's our second coordinate system. That's coordinate system B. And the x-axes are pointing in the same direction. You know, they agree on the direction of the x and they agree on the direction of y. We're just going to do that to simplify things a little bit, but it's actually really simple to, if one of those was skewed at some angle, you know, it's a really simple conversion to make it so that but we're going to do it so that the x's agree and the y's agree. And they're both measuring the location of this point. So let's say this is the, you know, the object. And I'll call it the object O. Okay, well, the position vector, the meaning of a position vector is a vector from the origin to the object that you're tracking, or the point of interest. And so this is the position vector of O according to this A coordinate system, okay? And this is the position vector of O according to the B coordinate system. And the notation that we're going to use is this is the position of O relative to A. And this is the position of O relative to B. So it's like a fraction bar in the subscript. Okay. Well, those coordinate systems can track objects, and they also can track the origin of the other coordinate system. So you could imagine, you know, I could draw the vectors like the position of this coordinate system B, talking about the origin, relative to A, or vice versa. So so this vector here, I'll move my B, is the position of B relative to A. and the notation before I talk about these relationships. So if I say the position of say A relative to B, that's not just referring to this A and B, but that's just generally what this subscript thing means. We call that the position of A relative to B, and it means the position vector of A that's observed by the coordinate system B. Okay. Well, look at this combination of, so we have these three position vectors, and by the rules of vector addition, you can come up with a relationship between these position vectors. You can see by the directions of the vectors that the position of O relative to A is equal to the position of B relative to A plus the position of O relative to B. Okay, you see that in the vector addition. And so you can see above that this relationship holds. The position of O relative to A, and I'm going to write it in the other order than I just said it, but it's still the same sum of vectors, is equal to the position of O relative to B plus the position of B relative to A. Well, you can think of it as vector addition. It's pretty easy to show yourself if you know what the correct relationship is between these just by drawing out the vectors. But an easy memory device, because you don't always want to have to do that every time you use this, is, so memory device is to think of fraction multiplication. So O over A is equal to O over B times B over A. Okay. So if you set up this relative motion equation and you set it up in a way that the subscripts satisfy that fraction multiplication, then you have them in the right order. Okay. Well, if this was only true with positions, I mean, it would still be useful sometimes. But this is the position relative motion equation. So think of that as equation 1 out of 3 of these equations. Well, what do you get if you take the time derivatives of both sides of this equation? So take d dt of both sides of 1, which you have to be able to do if this is true at every instant. And you get the velocity relative motion equation that says the velocity vector of the object relative to coordinate system A is equal to the velocity vector of the object relative to B plus the velocity vector of B relative to A. That's the velocity relative motion equation.
That notation, does that mean object at the end of both sides?
ddt?
No, on the end they're saying is that both sides are.
Oh, of equation 1.
Oh.
And then do it again, take the time derivative of both sides of 2. And you get the third one, that's the accelerations. So the acceleration of the object relative to A is equal to the acceleration of the object relative to B plus the acceleration of B relative to A. Third one. And that same memory device works for all three of those, position, velocity, and acceleration. If your subscripts work for fraction multiplication, then you have them in the right order, okay? So one thing that comes in handy sometimes is for any A and B, position of A relative to B is the negative position of B relative to A. This is true for coordinate system origins and objects, and the same is true with velocity and acceleration. In other words, if you write out your equation and it works for the fraction multiplication, but then you're like, oh man, I have the wrong coordinate system expressed in terms of the wrong thing, or I have the view of a coordinate system as seen by the object. That's a little bit of a hard thing to imagine, but it's fine. You just have to use, flip the sign and flip the subscripts. I'll show you, it makes intuitive sense if you look at the picture. Okay, so let's see why that works. So how does this work? So what if we wanted, so this right vector is the position of B relative to A. What if we got through our equations and we're like, oh, we want position of A relative to B? Well, that's the location of the origin of A as seen in this coordinate system. So that's just a vector from here to there. It's just the exact opposite vector. Just multiply it by -1. Okay. And if you do this in a funky way in one of your terms, but the fraction multiplication works out, and one of your terms says you want the position of A as seen by the object, it sort of makes sense if you imagine the object having another coordinate system on it, but it's a little bit of a funny way to think about it. But just flip the signs, flip the subscripts. Okay. So let's see how this works. So let's say that as an elevator accelerates, a passenger drops their keys. And a camera on the elevator, according to a camera on the elevator, the keys appear to accelerate down at 6.5 meters per second squared. What's the acceleration of the elevator? Okay, so there's the elevator. Here's the sides of the elevator shaft. And what we're imagining is up here, we have a camera in the corner of the elevator that really, to us, what that is a coordinate system. And that's moving with the elevator. Okay. And then fixed to the ground is another, yeah. Yeah. That's what it looks like. Um, that thing's supposed to be a key. And so there's this second coordinate system that I'm going to call G for ground. Okay. It has its axes in the same directions as the coordinate system on the elevator. Okay. And now I'm going to set up the relative motion equation. We're talking about acceleration, so I want the acceleration one. The acceleration of the keys relative to the ground is equal to the acceleration of the keys relative to the elevator plus the acceleration of the elevator relative to the ground. Almost always in these kind of problems, there's the ground, like some kind of fixed coordinate system, and then there's some vehicle or something, some object moving, and then something moving relative to that vehicle. And if you set it up as the term that's by itself is the motion of the object relative to the ground, it works out pretty easily. But otherwise, you can also just set it up in terms of, like, set it up with the left side having the variable you're trying to find, set it up with whatever crazy combinations you need to make the fraction multiplication work, and then just use these to flip the subscripts to make sense out of it. Okay. I'll show you that in a second.
Okay. And that's not this because elevator's on the right.
Yeah, that's not this because, so I did it as acceleration of the object relative to the ground is equal to acceleration of the object relative to the vehicle plus acceleration of the vehicle relative to the ground. And that way of thinking of it always works. Okay, so what do we know? In a coordinate system with the y-axis up, as long as this elevator is near the surface of the Earth, which it is, we know that this acceleration is 0, negative 9.81. meters per second squared. And that's equal to the acceleration of the keys as seen by the elevator, which was given in the problem. That's down at 6.5. So this is 0, negative 6.5. Plus the acceleration of the elevator relative to the ground. This is the one that we want. And now add 0, positive 6.5 to both sides, and you get that 0 is equal to negative 3.41 meters per second squared is equal to the acceleration of the elevator according to the ground. So that's the acceleration of the elevator. I always think of it as, like I said, the object relative to the ground is equal to object relative to vehicle plus vehicle relative to ground. But you could also do it like this. Remember that we're trying to find the acceleration of the elevator relative to the ground. And we have three things: an elevator, keys, and the ground. And now we just have to come up with a sum of two vectors that make that fraction multiplication work out. So this is going to be acceleration of elevator relative to the keys plus the acceleration of the keys relative to the ground. And then this one makes sense, the elevator relative to the ground. This one makes sense, the keys relative to the ground. The one that we don't have any expression for is the acceleration of the elevator relative to the keys. And so just use the flip the subscript, flip the sign thing. You get the acceleration of the elevator relative to the ground is equal to negative acceleration of the keys relative to the elevator plus the acceleration of the keys relative to the ground. And now we can fill in the things we know. The acceleration of the keys relative to the elevator is what we were given as 0, negative 6.5. And we're multiplying that by a negative 1. And then the acceleration of the keys relative to ground, that's just free fall. So 0, negative 9.81. And you get the same thing again.